Okay, this is the last filter, which is called additive filter. Okay, in additive filter, it's have been divided into two, which is additive local noise reduction filter. Another one is additive median filter. And actually, additive local reduction additive local noise reduction filter is actually it's related to, again, this one is related to kernel based neighborhood processing, or it can be under the same as mean family filter, while the additive mean filter is in under category of non-kernel neighborhood processing, or in other words is also known as order statistical filter. Okay, so let's discuss about the additive local noise reduction filter first. Okay, why they put in this one, these two category, these two complex, I can consider as a complex filter, and it's put in at the end of the discussion about this about the filter, is because these two is very special, because when we talk about the additive filter, like I mentioned in the previous chapter, actually you already see one additive mechanism. Okay, if you remember, when I discussed about the point processing, okay, point processing, I also said that histogram equalization, okay, is one of the additive approach. Okay, even histogram is a point processing, is does not we don't call that as a filter, but when we talk about some approach where is behave additively, meaning that it will change the mechanism depend on the input, depend on the condition of the input image. Okay, so that's why I said that histogram equalization is one of the additive approach, because it will change the transformation function additively according to the condition of the image. Is it low bright contrast image or low dark contrast image? So it will keep changing the transformation function. So we don't have to put effort in setting anything. Okay, the mechanism is behave additively. So that's why histogram equalization is one of the technique that additively change according to the input condition. So same goes to this filter. Okay, these two filter, okay, we put it aside out from the mean family filter and order statistic filter, because these two filter will behave additively, but the mechanism inside that filter is the fundamental is still the same. Where if you talk about the additive local noise reduction filter, it's there's a mean element inside. If you talk about additive median filter, there's a median element inside. Okay, just the advantage is where they can behave additively. Okay, so let's go to discuss detail about the additive local noise reduction filter. Okay, I just paste all the word here where I just copy from the slide, so easy for us to discuss. So the first thing you need to know is this filter. Okay, you need, before you can understand what how is operate and how to understand the formula. This is the formula of additive local noise reduction filter. You need to familiar with this notation or this parameter in local noise in additive local noise reduction filter. Okay, again, gxy is your input image, so I just draw some example here. Let's say this is your input image, so gxy is your input image. So of course xy is a location or the pixel location there, and then we have variant of the noise. Okay, you can see there's a two variants there. One is local variant and another one is variant of the noise. So in other words, what we mean by, you can also call this one as a global. Okay, this one can also, you can call as a global variance, because we have local variance, then you should also we have another one which is global variance. So what is mean by global variant is the variant of the entire image. Okay, meaning that if this is the set of matrix, all the pixels belong to the entire image, you take and then you count the variance. Okay, that is referred as sigma square n there, so which is your local global variance. Okay, another one you need to also know. Okay, then if we have a global variance, then what is local variant is this variant of, okay, this is your, okay, the variant of this number where the pixel which is inside the red surface, inside the red box there. Okay, you need to get the variant of that. So that is your local variance. And then we also have the mean local. So local mean is this one. You need to find the mean of this one. Okay, so you can see that we don't use this. We don't use, in general we always use mean as this one. But right now in this equation, this filter we notate the local mean as ML. Okay, we don't use this symbol to represent our mean because if you talk about this one, actually it's referred to global, means that if you want to find the mean of the entire image. Okay, but now it's we only considered as a local mean there, where actually you count the mean from the pixel where that pixel is inside this red box. Okay, so that is the item that we want to know. Of course, this one is not discussed, so because it's not involved in our additive local noise reduction filter, so that's why we don't have global means. Okay, we only have the local mean. And okay, once you're familiar with all the variable involved here, okay, again this SXY is keep sliding to the entire okay, from the start, like I mentioned before, if you talk about the all filter starting from the arithmetic mean filter, this one is keep sliding, so that's why you can achieve the output image which is our F hit. Okay, so okay, now once you're familiar with all these parameters, okay, this is how the filter is operate and how the filter is keep additively change. Okay, you can see that the filter gives some condition there. Of course, if you write the program, you can use the if else to do this one. Okay, because now anything fit into this filter, it will, it will test with this condition, 3 condition there. Okay, the condition number 1, if this one, which is our global variant, is equal to 0, then the output is equal to gxy, meaning that if the global variant, which is this one, this one is equal to 0, meaning that your image don't have any noise, meaning that your image is free from your image is free from noise. So if your image is free from noise, okay, so of course you don't want the filter to do something to change the information, so that's why actually you do nothing there. So that's why at the end you if you find out the global variance is equal to 0, then your then your F hit xy is equal to your gxy, meaning that you are not processing anything, you just pass through all the output values, all the input value to the output side. Okay, so that is the first condition. So let's say this condition is false. Okay, it's fail, and then it will check to the second condition. Okay, that assume, okay, if the global variant is not 0, meaning that the noise exists there in your image, then test the second statement. If the locals variant is more than global variant, then the filter output should close to gxy, because the high local variant indicate the presence of edge and thus should be preserved. In other words, if this condition is fulfilled, then your system this statement should provide the F hit xy must equal, or it doesn't matter, is it equal or close to your gxy, meaning that again, like the first statement, we don't proceed anything. if we find out our local variance is more than global variance. Okay, so where actually this condition happen, that's why I draw this picture, and I also draw some objects there. Assume this is the some practical image, okay, and you see this is the background and this is the object. Okay, this condition normally happen at this region, okay, this part. Okay, if the window or if the filter is arrived at this position, okay, you will get where this is the part where you get your local variance is more than your global variance. So why is this happen? Because when you achieve at this region, okay, of course something, because your window are already on, your filter is actually at the position of edge, okay, at the edge location where it, when we talk about edge or border, actually you have a two contrast region. One, some group of the pixels belong to the object, some group of the pixel is belong to the background. So in other words, because of significant different of intensity values there, if you count or if you calculate the local variant here, for sure you will get the variant, the local variant here is higher as compared to the global variance. So that's why this is the indicator to detect if your actually in this filter, in this local additive local noise reduction filter, they use this condition to detect, okay, to detect whether your sliding window is arrived at edge or border or not. Okay, because why they put this condition, because they want to detect that if they find out that the sliding windows is arrived at that area, then instead of applying the mean filter or arithmetic mean filter, because if you remember, if you apply the arithmetic mean or average filter, the typical average filter or arithmetic mean filter, what happened to the image? It will become blur. Okay, you can see that blur obviously at the edge of something, at the edge of object or at the boundary of the object, because that one originally is very sharp and now it become blur. So that's why in additive filter, in order to avoid that, what happened is actually when the sliding window is arrived at the edge, it actually don't proceed with mean filter or arithmetic mean filter. It will preserve the original value that's come from GXY. So that's why you can see that if we find out that this one is happened, then we don't proceed anything, seems like the first statement. Okay, however, for if the variance, the local variance here is equal to the global variance, this one is actually normally happen at this point, or any point where you have a plane surface like this one, okay, inside the object as well. Okay, meaning that if the window is go through the area where that area have a plane surface, whether that surface belong to object or that surface belong to background, that is where this condition happen, meaning that your local variance is equal to global variance. And this is where, if you find out this condition is fulfilled, then you need to apply, okay, then filter output of arithmetic mean value in that pixel, meaning that you will apply the arithmetic mean, okay, where you will apply the arithmetic mean, meaning that the same arithmetic mean or average filter, okay, of that window. Okay, that is what you do. Okay, so of course, if you want to develop this filter, then you need to, again, like I mentioned, if you talk about if you want to develop if you want to write the program, then you can use the if else. Okay, meaning that you have the if else, three if else that represent this three line, and then of course one things that I don't expose to you is how to write the image processing code from scratch. Okay, previously I show you you know how to write it by using the toolbox, where you already have the built-in function there. But actually when you want to slide the window, okay, if you want to build something from scratch, then you need to use the for loop. Okay, double for loop, meaning that one is a for loop to the x axis, another one is for loop to the y axis. So that's why if we keep moving, and inside that double for loop you must have this if else statement, three if else statement, okay, to do this filter. Okay, however, if you see the slide, actually another alternative way that you can do to you know to represent these three condition is by develop this code. Okay, because this code is actually represent these three condition or three statement here. Okay, so you can test one by one, meaning that, okay, for example, if the variance or the global variance equal to 0, means that this one is equal to 0. So what happened? So everything here becomes 0, and then so this one actually similar to this one. Okay, so means that you pass through all the input to the output. You don't do anything there. Okay, you are not process anything there. Okay, how about second statement? Okay, I just undo this one first. Okay, second statement, if this one bigger than this one, so meaning that this one bigger than this one. So if this one bigger than this one, meaning that the whole thing here is very small. It will result the small value. Okay, it can be 0 point something or 0.00 something. So if this one is very small and you are multiplying this small number with this statement, in other words, this statement is actually very small. Okay, it's very small, very small. So if something very small here, you do the minus operation with this one, meaning that it seems to be at the end, it's look like it's close to our g x y. So that is actually same as this statement. Okay, so how about the last statement, the last condition? Okay, if this one equal to this one, global variance equal to local variance equal to global variance. So if this one is equal, then this one will become 1. Okay, so if this one become 1, then this one is cancel each other. Sorry, this one is cancel each other. At the end, your f x y is equal to your ml. So what is ml? So ml is our local mean. Okay, if you talk about the local mean, actually mean of this set of number inside this red box. So if you compute the means of this set of number, actually that is look like your arithmetic mean filter, or if you convolve this region with average filter, so that is represent this thing. Okay, meaning that at the end, okay, this is the only condition that you need to apply the arithmetic mean filter. Okay, if you find out this condition or this condition, you are proceed with any whatever you have at the input side to the output side. So this statement actually, or this expression actually represent these three conditions.